So the goal of this lesson is to be able to predict boiling points of different organic compounds and to be able to make solubility predictions. The end of this lesson, fractional distillation, is been on every diploma I've ever seen. So the last slide, the ending of this lesson, is really important to take note of. So in order to make predictions on boiling points and solubilities, we have to understand the three forces, intermolecular forces that we might see. So the first force, which every molecule has, is London dispersion forces. This is caused by random motion of electrons. Okay. Even if there is no polarity in a molecule, there'll be electrons. They'll be randomly moving. They'll be attracted to the nucleus of another atom. That will cause some attraction between one molecule and another. Now, the main thing you need to remember is the more electrons something has, the stronger the London dispersion forces will be. Okay. So if you have methane versus ethane, so I'm doing 2n plus 2 to get the ane hydrogen count. Okay. We don't actually have to count electrons to know which molecule is going to have more. The C2H6 has more carbons, it has more hydrogen, so there is more electrons in C2H6 than there are in CH4. More electrons will cause a greater London dispersion force between a whole bunch of ethanes compared to a whole bunch of methanes. So that's our first force, and essentially the bigger the hydrocarbon gets, the higher you're going to see its boiling point get. Second force, the one we use the least, is dipole-dipole forces. Not because it's unimportant, but it's not typically in this unit what we'll be focusing in on to break our ties. Dipole-dipole forces are caused by permanent polarity, permanent positive and negative ends. We see a fair bit of polarity in fluoromethane. We have a fluorine atom that is very electronegative, has a great attraction for electrons. In your Alberta Chem 2030 data booklet, you've got electronegativity values right in your book, and fluorine is 4.0. You're not going to need to look these up, but this was the Chem 20 theory that we used to predict electronegativity. Carbon is 2.6. Okay. These values from your data booklet tell you how strongly atoms attract electrons. So fluorine has a greater attraction for electrons. In Chem 20, we would have put an arrow to show that polarity. The bigger the arrow, the bigger the electronegativity difference. Okay. The arrow pointing towards the more electronegative end. So fluorine has a greater attraction for electrons, 4 versus 2.6. So we have our slightly negative end and our slightly positive end. This is all the Chem 20. You just need to realize that there's a permanent dipole here. There's a negative end and a positive end. So this molecule, fluoromethane, has London dispersion forces, and on top of that, it has dipole-dipole forces. It has two different types of forces. The last force from Chem 20 was hydrogen bonding. And this one's going to be pretty important. This force is present in some of our families, but not all, not most. Okay. Hydrogen bonding is really just an extreme dipole, a positive and negative end. Okay. And we only see an extreme dipole in 3 examples: when there's an O to an H, an N to an H, or an F to an H. Sometimes a kind of joke or saying, about hydrogen bonding is hydrogen only wants to have fun, but it's F-O-N, not F-U-N. You get hydrogen bonding with F-O and N. Okay. Now, that was for Chem 20. We're doing organic chemistry, so there's no carbon. We don't have any HF in this unit. Okay. We're not studying the nitrogen-based compounds, unfortunately. I wish we were, but they're not in the curriculum. But we've seen OH in two different families. We've seen them in the alcohols, and we see them in the carboxylic acids. So you have to watch out for hydrogen bonding in two of our families. Okay. So the simplest alcohol I could draw would be methanol. That has all three of the forces. It has London dispersion forces, it's polar, and it's got that extreme polar bond, the O to the H. We also have it in methanoic acid. That's how you would name this. One carbon meth, drop the E at oic acid. We have this piece that can hydrogen bond, and then we've got another very polar piece. Okay. So alcohols, a lot of forces, carboxylic acid, even more so. We don't have hydrogen bonding in any of the other families that we've covered within this curriculum. Okay. So a couple examples before I'm going to do a forces by family summary. And then I'll ask you to apply your knowledge and do some ranking. I'm going to do some ranking first. In 2 slides, you'll do some. So rank the following from lowest boiling point to highest boiling point. So lowest boiling point would have the fewest forces. The highest boiling point would take the most energy to separate them. And what would take the most energy to separate would be the one of those three that has the most forces. Now, to guide us with a little bit more visuals, I'm going to put the molecular formulas underneath. So hexane, hex is C6, ane is a 2n plus 2 pattern generic formula. So 6 times 2 is 12, plus 2 is 14. Meth is 1, and we don't write 1s. C1, H2n plus 2. There'll be 4 H's. And last, butane, C-but is 4, but that's a triple bond, so it's 2n minus 2. So 8 minus 2 is 6. So we want to rank these. We want to think of London dispersion forces, dipole, dipole, and hydrogen bonding. So all molecules have London dispersion. Now, hopefully your Chem 20 teachers had said something about hydrocarbons. Does anybody remember anything about polarity when you have just C's and H's? When you have C's and H's only, they're always nonpolar. So it could be C100, H200. Okay. There will never be a positive and negative end to our hydrocarbons. So none of these are going to have dipole-dipole forces, and there's no way it can have hydrogen bonding because it's just C's and H's. So the only forces we have is London dispersion. So if you notice that right away, you wouldn't even maybe make a big list. You just realize there's only London dispersion to consider. Okay? The smallest molecule with the least electrons has the least forces. The biggest hydrocarbon with the most electrons will have the most forces. So let's reread the question. Rank the following from lowest to highest. So what has the least boiling point, the least forces? That'd be the least electrons. So that would be our methane. Second on our list, as we head towards the highest, would be the second most electrons. So that would be our C4. And the highest boiling point would have the most London forces, the most electrons. That would be our hexane. So if you have a list of just hydrocarbons, you're just ranking them ultimately by size, which is a proxy for electron count. My second ranking is only going to be between two molecules, methanol and methane diol. Now I'm going to draw these two to help us and then make that list again. Methanol is alcohol. There's no number because it would have to be in the one position because meth is just one carbon. Methane diol. Meth is still just one carbon. But we've got a di, meaning there's two hydroxyl groups. There's no number because they both are in the one position. So it's kind of methane 1,1 diol with the numbers dropped. Okay, now we got to compare these two. If you're not sure, make a list. Analyze the forces. You've got to go through this even if you just go through it in your head. Well, everything has London dispersion forces if it has electrons. Okay. Both of these have one of these bent hydroxyl groups, okay, which causes there to be a dipole. So there'll be dipole-dipole forces. And is that OH one of those special dipoles? It is. It's, you know, H has fun, F-O-N, the O. Okay, so that is that hydroxyl group will cause hydrogen bonding. Okay, so we've got all the forces. So we're going to have to look and break some of the ties. To simplify things within Chem 30, your test questions are either going to have a difference with London dispersion forces, or you're going to look at the third on my list, you're going to look at hydrogen bonding. Dipole-dipole forces are not going to be the force that's going to break the tie. So look at the first and the last and look for differences. So is there any difference between London dispersion forces between these two molecules? Does either one have more electrons? They both have one carbon, so that'll be a tie. They both have 4 H's, so that'll be a tie. But the diol has an extra O. So the diol is going to have more electrons, so there's going to be more LDF. Okay. So our first force is greater in the diol. And let's look at hydrogen bonding. Okay, we want to look at the first force and the last force to kind of break our tie, or to see which one's going to have more forces overall. Well, the methanol has 1 OH, so that's going to hydrogen bond, but the diol has 2, and they don't cancel each other out. Okay, I don't want to go back and go through all of Chem 20 bonding, but due to the bond angles, hydroxyl groups never cancel out the polarity. It doubles it. Okay. So hydrogen bonding, we're going to get 2 times the hydrogen bonding in the diol compared to the methanol. Okay. So the LDF is bigger with the diol. The hydrogen bonding is bigger with the diol. We looked at those 2 forces, and the diol is going to have the most forces. We're not going to dive into dipole-dipole. Those 2 will be enough. Okay. So this one will have the greater boiling point, okay, and melting point. Okay. So it's going to take more energy to boil the diol than it does the methanol. It's going to be a higher temperature. That's what I mean by greater boiling point. So that's some examples. Let's summarize things, categorize things. So we're going to have a big category. I've kind of already mentioned the main outcome of this category. I've put all the hydrocarbons together. The anes, cycloanes, the enes, the cycloenes, the ines with the triple bonds. Benzene has just C's and H's. So that's my list here, C and H only. Okay. All hydrocarbons. Okay. They are all nonpolar. Okay. They all have London dispersion forces only. Okay. And you can separate them out by essentially size, but you're really looking at electron count. So that covers 5, 6 of our families that we've looked at. Okay. The only quirk you'll get here is you could have 2 hydrocarbons that have a tie for electrons, the same molecular formula. Okay. And there's a word for that, which I want us to think about. When did we have 2 different structures, but they're the same molecular formula? There was a vowel starting term for that. Okay. Those would be isomers. Okay. If you have 2 isomers that have the same formula and the same electron count, okay, you're going to have to look at branching to kind of break the tie. If 2 hydrocarbons have the same molecular formula, call those isomers. Okay. The more branched hydrocarbon will have the lower boiling point. This would have been a slight nuance in Chem 20, and I'm going to emphasize it a little bit more here with a couple drawings. I'll hide my word isomers. I'm going to do a couple isomers of C4H10 and compare the boiling points of a couple of those. Okay. This was the same isomer example several lessons ago. Okay. Okay. So the more branched, the lower the boiling point. If you don't have any branching, the isomers can get really close to each other and have the maximum forces. So I'm going to do the straight chain, no branches. 1, 2, 3, 4, lift my pen. Okay. Now there's H's coming off that line structure, but hydrogens are really small. There's only 1 proton in them. Okay. I'm going to draw a few more C4H10s. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. See how close I can line them up if there's no branching? So they're not very far apart. So the London dispersion forces have a small distance. The bigger the distance, the less the effect of the charge. So this would have a greater boiling point compared to the branch version that I'm going to do. The branch version, the molecules are going to be further apart, and the forces will be weaker because of that distance. So that's the straight chain. I'm going to do methyl propane. 1, 2, 3. Then I have to stick in a branch to get C4H10. And now, if I draw another one, I need some distance in between because that branch is going to push them apart. And if I do another isomer, I only really have room to do one more. That branch, again, is spacing them out. So this one will have the lower boiling point. It's not a, normally we're looking at forces, but here's the distance consideration. Okay. To try to make sure everybody sees the 4 carbons, I'll use my circle strategy to make them pop out. 1, 2, 3, 4. Okay. In our methyl propane isomer, 1, 2, 3, 4. Okay. They're both C4H10s. Okay. Now I spent some time here, but by far the most important is the top. Just realizing all hydrocarbons are nonpolar, and the more electrons it has, the greater the forces. Okay. Now we're going to fly through the rest of the families fairly quickly, but they're really important to remember the trends. Organic halides, we're going to have 2 categories to talk about. Some of them have LDF only, the minority. Most of them have LDF and dipole-dipole forces. So your brain has to figure out which of the 2 categories do we have. So I'll do an example. When do we have no positive negative end in an organic halide? That would be because the halides are nice and symmetric around a carbon. So if we had tetrafluoromethane, there's no positive and negative end because of all 4 of those F's. There's 4 polar bonds that cancel each other out. Okay, I'm using a lot of Chem 20 speak. I could have a carbon-carbon double bond, and there has to be the same halogens all the way around. If I have 4 chlorines, though 4 CH bonds will cancel each other out. So this won't happen a lot, but you can have LDF only. What is way more common is an organic halide with polarity. We don't have 4 of the same halogens all around a carbon, and then the polar bond can't get canceled out. This very polar bond is not canceled out by those CH bonds. Now I'm drawing that flat. You have to realize, going way back to Chem 20, that what I drew is really a tetrahedral shape in 3 dimensions. So I'm trying to take something that has 109.5 bond angles and flatten it out. Okay. Okay. So that's organic halides. So we've got all these hydrocarbons that have LDF only. We've got organic halides that fit into 2 categories. Most of them are polar on the right, but occasionally that polarity is canceled out like we see on the left due to symmetry. Now we're on to our alcohols. And then last, I have carboxylic acids. Alcohols, these are kind of a nice family for Chem 30 because the alcohols are going to have all the forces. They're going to have LDF, they're going to have dipole-dipole forces, and they're going to H bond because alcohols have a hydroxyl group. So there's only one category. You see an alcohol, you know you've got all these forces. I'll stick up methanol as an example again. And there's that very polar bond. That gives it dipole-dipole forces. One of the several polar bonds, but that's the most polar that causes the hydrogen bonding. Last, we have carboxylic acids. They're also fairly nice because there's only one possibility. Carboxylic acids are going to have all the forces. I'll do the drawing first to highlight the forces. There's methanoic acid. We've got that extreme dipole-dipole, which is called hydrogen bonding. We have LDF, we have dipole-dipole, and hydrogen bonding. So we really just have to watch those organic halides that have two different lists. So if the electron count was similar, you're going to see the most forces with carboxylic acids. Because carboxylic acids have hydrogen bonding, which would tie the alcohol, and it's got this big dipole-dipole. So carboxylic's kind of at the top of our list, then alcohols, okay? Then probably the organic halide if it's polar, and then you'd be looking at the hydrocarbon. Okay? Again, assuming that all the electron count is the same. Okay? If you had a whole bunch of alcohols, okay, hydrogen bonding would be a tie. You have ethanol, methanol, propanol. They all have one OH, so then you'd look at London dispersion to break the tie. Okay. So let's see how you can work on making the list and comparing these examples. So hexane versus butane, you're just circling, determine the species with the higher boiling point, okay, or melting point. They have the same trend. Okay. Just think of what has the higher boiling point. Hexane, butane, methane, water, 1 bromopropane versus 1 chloropropane, and nonane versus 3-ethyl heptane.